gradient flow to minimize KL divergence or relative entropy in the space of distributions with respect to the W2 metric. So in this perspective of sampling optimization, to draw a sample from some target distribution nu is equivalent to minimizing some objective function, say KL divergence, which is minimized at that target distribution. So in this view, Langevin dynamics that we study is the gradient flow to minimize this objective function, and the proximal sampler, the algorithm, is approximately the proximal gradient method of discretizing the gradient flow. More concretely, in this view, the KL divergence plays the role of objective function. Let me call that this curly f. The Wasserstein distance is playing the role of the metric on this manifold of distributions. And the Fisher information that we are studying has the role of the squared norm of the gradient of the objective function under this Wasserstein distance. So the definitions of the distribution satisfying strong log concavity is saying that the negative log density is a strongly convex function. And we say that a distribution satisfies log Sobolev if for any other distribution rho, the KL divergence is upper bounded by the Fisher information. Now, the optimization meaning of these conditions is as follows. Strong log concavity of the target is actually equivalent to saying that the KL divergence objective function is strongly convex on this manifold. And log Sobolev is equivalent to saying that the KL divergence satisfies this PL condition, the Polyaklo-Jasiewicz condition. And we know that both of these conditions are sufficient to get fast convergence in optimization. And what's known also is that strong log concavity implies log Sobolev, but log Sobolev is much broader. So it is stable under perturbation and mapping. So what it says is that we can in fact sample efficiently from distributions which are slightly non-log concave like this using this Langevin dynamics. So more concretely, these are classical results that along the Langevin dynamics in continuous time, if the target is strongly log concave, then we have this convergence guarantee in W2 distance. Under log Sobolev, we have this exponential convergence guarantee in the KL divergence in the function value. And what we will study in this talk is that under strong log concavity, turns out we also have exponential convergence guarantee in Fisher information. So all of these are still in continuous time for the idealized Langevin dynamics. And the main question is, what can we say in discrete time for the algorithm? To answer that, we draw this inspiration from the continuous time dynamics and discrete time algorithms. For optimization, recall that if we have gradient flow dynamics in continuous time, there are many ways to discretize. The basic forward discretization is the gradient descent algorithm. And we also have the implicit, the backward method called the proximal gradient method, which requires solving this implicit optimization problem in each iteration. So this is for optimization. For sampling, the analogous picture to this slide is the following. In continuous time, we have the Langevin dynamics, which is playing the role of gradient flow. A basic discretization that looks like gradient descent is called the unadjusted Langevin algorithm. This is simple, but turns out it is biased, so it does not converge to the correct algorithm. So what we will study in this talk is this new algorithm called the proximal sampler, which I will describe more. And it looks like an approximate version of the proximal gradient method. So more concretely, here's the proximal sampler algorithm. If we want to draw a sample from e to the negative f on the x space, what we do is let's define a joint distribution on the xy space via the following. So exponential of the negative f of x, the original target, plus this quadratic regularization with some step size eta. And the important property here is that in this joint distribution, the x marginal is the original target e to the negative f. So if we can sample from this joint distribution, we can just return the x part, and that will be the correct sample. So the proposal is, let's run an algorithm to sample from this joint, and the algorithm is the Gibbs sampling. So this gives what's called a proximal sampler, which was proposed by Li, Shen, and Tian at COLT a few years ago. So it is a two-step algorithm. First, in the forward step, from x we draw y given x, and this part is actually easy. This part is actually Gaussian. And then in the second part, from y, we draw x given y from the conditional. This is the difficult part that's called the restricted Gaussian oracle. So it turns out that under some condition, only when f is smooth and with the step size small enough, then turns out we can sample from this RGO, this backward conditional, in constant number of queries. So the question becomes, what is the outer iteration complexity of this algorithm? And what we showed in the previous work also is that this algorithm can be seen as an approximate proximal discretization of the Langevin dynamics. So in the original paper by Li Xuan and Tian, what they showed was that under strong lock concavity, the proximal sampler has this exponential convergence guarantee in W2 distance. And this matches the continuous time result from Langevin dynamics that we saw. The optimization meaning of this one is that for gradient flow, under strong convexity, we have exponential convergence guarantee in the distance. And in discrete time, we also have exponential convergence guarantee along the proximal gradient method. In a paper a few years ago at Gold, what we showed was that for proximal sampler, under log Sobolev, we also have this exponential convergence guarantee in KL divergence, matching continuous time. And the optimization meaning of this one is that for optimization, under PL condition, the function value is decreasing exponentially fast in continuous time and discrete time. Now, the main question in this work is that what about for Fisher information? In continuous time, we know we have exponential convergence guarantee and a strong lock concavity. In discrete time, what can we say about the proximal sampler? And the optimization analog of this one is that under strong convexity, we have exponential convergence of the gradient norm in both continuous time and discrete time. So our main result is to show that, in fact, this bottom right corner here can be completed. And what we showed was that along the proximal sampler, under strong lock concavity, the Fisher information also converges exponentially fast with a rate that matches continuous time, also matches optimization. And this implies an iteration complexity that if we want to run proximal sampler to sample to get small epsilon error in Fisher information, the iteration complexity is d times kappa, condition number, times this log 1 over epsilon. And this matches with the proximal gradient method for optimization up to this factor of d. And a quick word about the proof is that previously for the KL divergence, what we showed was basically strong data processing inequality along this forward channel and backward channel to show contraction of KL divergence. What we show in this work is as a similar method that along this forward channel, along the Gaussian channel, the Fisher information in fact contracts by this factor. So this looks like KL divergence up to a factor square. And this says that we have strong data processing inequality in Fisher information under strong lock concavity. Now, one surprising thing is that, in fact, without the strong lock concavity assumption, even weak data processing inequality is not true, whereas it's always true in KL divergence. Right? So in fact, we can construct two distributions such that if you pass both of them along the Gaussian channel, the Fisher information can increase first, like what's shown in this third plot here. And then in the second step, in the backward step, we also show that we have weak data processing inequality for Fisher information. Combining the two, we have the overall iteration complexity for, we have the overall convergence guarantee for the Fisher information along the proximal sampler. So to summarize, in this talk, we studied the convergence guarantee of the proximal sampler in relative Fisher information under strong lock concavity. And this completes the square here, matching the optimization and the sampling results in both continuous time and discrete time. And the proof technique proceeds via STPI. So thank you for your attention, and happy to answer any questions.
We will have the next speaker set up, and in the meantime, any questions for Andre? I'll ask them. So I guess, are there any cases that we know of where choosing a different metric for the proximal sampler might make sense and might give some benefits for algorithmic benefits?
Yeah, so the question is, does it make sense to choose different metrics for proximal sampler? Yes, so in this kind of figure, so this result has been shown also for Mérieux divergence, chi-square divergence, in fact for all phi divergence, and it's just depending on what kind of assumption we're willing to put. And for Mérieux divergence and so on, I think there are applications for individual privacy and for other applications.
The next speaker as well.
I am the next speaker.
Up next, we're going to have Andre tell us about min-max Langevin dynamics.
Okay, let me switch. How do I do this?
Nice.
Should I start? Okay. Hi again, everyone. Still Andre Wibisono from Yale, but now this is joint work with my colleagues Yang Tai from Yale, and also my students Sid Mitra and Peter Wang, who's sitting here in the audience. So this talk is about the convergence of min-max Lanchovan dynamics and algorithms. So this is for game theory instead of optimization and sampling from the previous talk, but there are still a lot of similar techniques. So the problem here is that we want to study this min-max problem on the space of distributions, where the payoff function looks like the following. So this payoff function f looks like the expectation of some base payoff function v over x plus y, and then plus this entropy regularization. So here in this work, we study this problem when the base space x and y are the Euclidean space. And we also impose this entropy regularization with some fixed regularization parameter tau. And the goal of this problem is to find what's called the equilibrium distribution, which is also a product distribution, say this nu star xy, that satisfies the following inequality for all distributions rho x and rho y. Right, so this looks like the usual equilibrium definition in game theory. And for this specific objective payoff function, turns out that we can solve this condition, and the equilibrium distribution has to have the following implicit density. So the density of x is a function of some expectation of the density of y, and vice versa. And the main question is, how can we sample from this equilibrium distribution? And the issue is that we don't have an explicit formula for the density, only that it satisfies this fixed point equation. And what we will study is the most basic classical Wasserstein gradient flow, which becomes this min-max Lanchovan dynamics for this problem. And this problem has a lot of recent related works, including the following. Using a lot of different techniques and modifications of the algorithms to show some convergence guarantee. However, the convergence guarantees for the simple min-max gradient flow turns out to still be missing. And this was actually proposed as an open question last year at COLT by Guillaume Wang and Linaik Chizat. And recently, there was a paper by Conger et al. That studies a more general setting of games on distribution, zero-sum and cooperative game. And one of the results is, in fact, to answer this question, under strong convexity in the continuous time mean field setting, which is the same as ours. However, what we do is we also prove bias convergence guarantees for the finite particle discretization and the discrete time algorithm. So let me give a brief overview of here are the three systems we study. The first part is the min-max min-field Lanchovan dynamics. This is the true min-max gradient flow in the Wasserstein space. And then we will study the finite particle discretization in continuous time, and then finite particle discretization in discrete time. Let me first describe the results for this first part here for the min-max min-field Lanchovan dynamics. So again, for this min-max problem on the space of distribution, suppose we run the min-max gradient flow on the space of distribution using Wasserstein metric. So formally, the x part should flow along the negative gradient of f, the gradient in the x direction, and the y part should flow in the positive gradient of f, gradient in the y direction. Under the Wasserstein metric for this objective function, it turns out that this system of gradient flow is implemented by the following system of stochastic differential equations in x and y. However, this is a mean-field interaction in the sense that the x evolution depends on the expectation over the y distribution, and the y variable also evolves following depending on the expectation of the x distribution. Because the dependence is only via expectation, x and y are in fact evolving independently, so the distribution is a product. And what is nice here is that if our base function v is strongly convex, strongly concave on the base space, then when we lift to the space distributions, this payoff function f becomes strongly convex, strongly concave on the space of distribution. And then we can expect that the min-max gradient flow to converge exponentially fast, and that's what we show. But to state the result, we need the following notion, what's called best response distribution. So if we have some distributions, rho x and rho y, we define the best response distribution, nu x and nu y, to be the following. So nu x is the argmin of this payoff function when we plug in rho y as the second argument. And in fact, we can solve this problem, and we know that the best response has the following explicit density function. And similarly, the y best response has the following formula for the density function. Now, under this definition, we can reformulate our problem and say that the equilibrium distribution is in fact a fixed point of this best response map. And moreover, the duality gap of the game is expressed as the KL divergence between our distribution and the best response distribution. So therefore, to prove convergence to the equilibrium distribution, we want to show that this duality gap converges exponentially fast. Now, under that definition, the mean field min-max Langevin dynamics can be rewritten as, in fact, the Langevin dynamics targeting the best response distribution, which is also evolving over time. And as we saw in the previous talk, this can also be seen as the Wasserstein gradient flow for KL divergence with respect to this best response distribution, which is now also evolving over time, rescaled by this regularization parameter tau. And again, if the base function is strongly convex, strongly concave, then this best response distribution is also strongly log concave, and therefore we can expect that this Wasserstein gradient flow to converge exponentially fast. And that's our first main result. So we show that along this continuous time mean field dynamics, at each time t, the phase information between our iterate and the best response distribution is converging exponentially fast to 0. And this implies that the iterate also converges exponentially fast to the equilibrium distribution nu star. Right? So the duality gap is KL divergence to the best response, and that is an upper bound to KL divergence to the actual equilibrium distribution. So this shows that in this continuous time at ELS limit, we have exponential convergence guarantee. And then the question becomes, what happens when we want to implement this as an algorithm? So we have to discretize as particles and then discretize in discrete time. So first, let me describe the results for this finite particle continuous time distribution dynamics. So the dynamics looks like the following. So we replicate the system into this, every player X becomes n particles, and every player Y becomes n particles. And we have these two n particles that are evolving following this interacting particle system, where we replace the true expectation by this empirical expectation of our particles. So now this becomes a truly interacting particles, no mean field interaction. So X and Y are correlated. As a result, even when V is strongly convex, strongly concave, this system will converge to its stationary distribution, which is not the independent product of the equilibrium distribution. So the system is biased, but we can control the bias. And that's our second main result. So we show that if the potential, if V is strongly convex, strongly concave, and smooth, meaning the second derivative is bounded, then if we define kappa to be this condition number L over alpha, then along this finite particle interacting dynamics, the KL divergence between our iterates and the equilibrium distribution is bounded by one term that goes to 0 exponentially fast, plus an asymptotic bias term. And what we note here is that the asymptotic bias does not scale with n, even though both of these distributions live in this huge n-dimensional space. And then this implies that when we take the average particle, we get a good convergence guarantee. But this is still in continuous time. And finally, we study the discrete time implementation of the algorithm. And what we do is, this is the simple forward discretization of the dynamics, where we just replace the drift term by a simple forward step, like gradient descent step, plus independent Gaussian noise. And again, this become a pure interacting particle system in discrete time. And what we can show is that even if the payoff function V is strongly convex, strongly concave, and smooth, this particle system will converge to its stationary distribution, which is biased, and we can control the bias, but now the bias scales with step size times dimension times number of particles. So concretely, along this interacting particle system, if the step size is small enough, then the KL divergence between our iterate and the independent product of the equilibrium distribution is bounded by two terms. The first term goes to 0 exponentially fast, like in continuous time, and the second term is the asymptotic bias term. And now we see that this asymptotic bias scales with n, number of particles, and also with dimension. And then when we try to output the average particle means that among these n particles, we pick one particle at random and output that as our result. Then this implies that we get 1 over n times the right-hand side here. So then from this, we can extract iteration complexity to say that if we want to reach KL divergence small, less than epsilon, that it's enough to run this finite particle system with eta step size, which scales with epsilon and these problem parameters, and the number of particles scales with 1 over epsilon, and k, the number of iterations, to scale with this dimension, condition number, and epsilon. And here we have this polynomial dependence on 1 over epsilon because this algorithm is biased. Right. Okay, to summarize, in this problem, we studied the min-max scheme of the space of distributions over the Euclidean space with entropy regularization when the payoff function is strongly convex, strongly concave, and smooth. We studied the following 3 systems of dynamics. The first 2 are in continuous time, and the first one is in mean field dynamics, converges exponentially fast with the equilibrium distribution. And the last 2 dynamics are for the finite particle systems, and we show that they have this bias convergence guarantee. So our result answers the open question by Wang and Chizat in the special case under strong convexity. And there are many interesting questions, including what happens without convexity for the manifold setting. So thank you for the attention. Happy to answer any questions. I'm done.
If I can ask one, so what is kind of the analog here, I guess, of something like a functional Sobolev inequality, something like a log Sobolev inequality, instead of like in lieu of strong convexity?
Yeah, so the question is, what is the analog of log Sobolev inequality? Good question. I'm not sure. I think one answer can be that, suppose we want to say that this equilibrium distribution satisfies log Sobolev instead of assuming that V is very convex, very concave. And then can we show guarantees only assuming log Sobolev? That we don't know how to answer because part of our analysis here involves some synchronous coupling. So we need strong convexity.
What goes wrong in the constraint setting? Like if you have simple constraints like simplex or all?
Yeah, thank you. The question was goes wrong in the constraint setting, and in that case, even the base continuous time flow has to be redefined because because this base continuous time flow has a Brownian motion which goes everywhere. So if it's constrained, we need to either reflect or project or do something else here. So yeah, so we have to do a projected gradient flow or something here.
Okay, let's thank Andre again.
Thank you.
Okay, next up we have Yu Tue, who's going to tell us about query complexity sampling from non-local distributions.
Okay, thank you for the introduction. Hi everyone, I'm Yu He from Shanghai Jiao Tong University, and this talk is about the query complexity of non-log concave sampling problems. And this is a joint work with Chi Hao. And in this work, we consider distribution over the d-dimensional real number space, and its density function is proportional to e to the minus f, and we call f a potential function. So here is an example of the density function and its corresponding potential function. And we want to sample from this distribution, and what we have is a query access to the value of the potential function and its gradient. We want to generate a sample from mu with epsilon error in total variation distance within as few queries as possible. And of course, we have some assumptions on the distribution. We assume it to be L-log smooth, and we assume it has a bounded second moment. And these two assumptions are commonly assumed in sampling works, and they are very basic assumptions. And in 2018, in the work of Ge, Li, and Ristetsky, they proved an exponential lower bound for this problem. And in 2024, In the work of He, Rojas, and Tao, they proved this upper bound use diffusion algorithms. And here the xk is the particle in the kth iteration of the algorithm. And also in 2024, Huang, Zhou, Dong, Ma, and Zhang proved a quasi-polynomial upper bound. Here, quasi-polynomial is with regard to the dimension d. And it seems that this quasi-polynomial upper bound breaks that exponential lower bound. So it's strange, but actually they need an extra requirement. They assume the distribution during the OU process starting from mu is also L log smooth. So the motivation of this work is to understand the query complexity under the two basic assumptions, and we also want to compare the standard smoothness condition and this strengthened smoothness condition during the OU process. In this work, the main contribution is to prove an almost tight query complexity bound for this problem, both an upper and lower bound. It's exponential in D, of course, and if we fix D, it's polynomial in L, M, and epsilon. And now if we only focus on the dependence on epsilon, there are some interesting corollaries. The first one is that this result, especially the lower bound, implies that poly log 1 over epsilon samplers do not exist. But in contrast, in log concave sampling problems, we know Metropolis-Hastings algorithms can achieve a query complexity of poly log 1 over epsilon. But this is impossible for non-log concave sampling problems, even when D is a constant. And the second point is that this lower bound implies functional inequalities like Poincare inequality do not hold in general. Because we know if a distribution satisfies a Poincare inequality, we can find a sampler with poly 1 over epsilon query complexity. But here, this lower bound is 1 over epsilon to the power of D. And beside this bound, we also compare the two smoothness conditions. Due to the contrast of the quasi-polynomial upper bound and the exponential lower bound, we already know there are fundamental difference between these two conditions. And in this work, we construct a specific kind of distributions, which are O1 log smooth, but it can be omega d log smooth during the OU process. And this further confirmed the result. This further confirmed the difference between the two conditions. And we also study the non-convex optimization problem. We prove a lower bound to approximate the global minimizer of F. And it turns out that non-convex optimization is harder than non-log concave sampling. And now I will introduce the techniques to prove the lower bound. The key idea to prove the lower bound is to construct more hard instances that we cannot tell them apart. For example, we perturb the Gaussian with a small needle, and as the main body of these two distributions are the same, they have the same potential functions. So the only way for an algorithm to distinguish them is to query the points in this needle area. And we can see a two-dimensional Gaussian to have more intuition. Here, the darker place means the larger density value. So we use this graph, we use this figure to represent a two-dimensional Gaussian. And here, a small circle corresponds to a needle area here. If we perturb the density in this small circle, we can construct a hard instance. So a small circle corresponds to a possible hard instance. And if an algorithm wants to output the right answer with high probability on all these possible hard instances, it should almost query each circle to find out which is the perturbed one. So if we can pack more disjoint circles, we can construct more hard instances, and we can prove a larger lower bound. We actually reduce that problem to a packing problem, and of course, we require the hard instances we construct to satisfy the smoothness condition and the second moment condition. And this is basically the idea used in the work of Geli and Ristetsky to prove that exponential lower bound. And in this work, we want to prove an even stronger one. So we want to pack more disjoint small circles. What can we do? The first try is can we put the needle farther away so the area, the space to insert possible needles is larger, so we can maybe insert more needles. But this is not allowed because we require the distribution to have a bounded second moment. There cannot be a mass in a faraway place. And another try is to use taller and narrower needle, so the radius of the small circle is smaller. So we can maybe insert more, we can put more disjoint small circles. But this is also not allowed because we require distribution to be L-log smooth, and such sharp curve is not allowed. And the main contribution of this work is to find that it's not the best choice to perturb a Gaussian, but it will be better to perturb a distribution like this. It also starts from a Gaussian, but we lift the two sides up. As we can see in this figure, another reason that caused this sharp curve is the density of the Gaussian decreases too fast. So if we use this kind of distribution and we can perturb it with taller and narrower needle and still guarantee the log smoothness. And finally, we can prove the lower bound we want. So the idea to prove the lower bound is just to find a needle in a haystack. And for the upper bound, if we want to sample from a distribution like this, it's a non-log concave distribution or multimodal distribution. The most difficult part is the low valley that separates the modes. And in other words, if we want to establish a query complexity upper bound, and a possible idea is to prove a functional inequality for it. So if we compare the potential function of the target distribution and the potential function of a Gaussian, which is a quadratic function, we know that if the difference between these two potential functions are bounded universally, then we can prove a functional inequality like the Poincare inequality for the target distribution. But due to such large gaps, we cannot derive a universal bound for the difference between the two functions. So what we do in this work is to do a truncation. We just truncate the area with large gaps and construct a new potential function and a new distribution. And for the new distribution, we can prove a Poincare inequality for it. And because we only modify the potential functions of this area, which has a small mass, so the two distributions are similar. So if we want to sample from the left distribution, we can just sample from the right distribution as a substitution. So the idea of the upper bound is to construct a similar but simpler distribution. And here comes to some future directions. The first open problem is that what is the real tight query complexity bound? We know it has such a form, but we don't know what is the constant in the exponent. What is the constant coefficient in its exponent? We guess it might be 1/2, but we don't know how to prove it yet. And another interesting problem is that, as we know there are differences between the two smoothness conditions, the standard one and the strengthened one during the OU process. But in many works about diffusion models, they assume the second strengthened smoothness condition. So we want to find out to what extent a smoothness process can maintain that a diffusion process can maintain that smoothness condition. And we also know if we assume the strengthened smoothness condition during the OU process, we already have quasi-polynomial upper bounds. And we wonder how well we can do under that condition. Do we have polynomial samplers? And fortunately, in one of our ongoing work, we can establish a polynomial query complexity upper bound under that strengthened smoothness condition during the OU process. And that's all about this talk. Thank you. Do you have any questions?
Hi, quick question. So I guess your bound improves as D grows larger than LM, right? Like in the sense that there's a D in the denominator. So in that regime, is there like an alternative algorithm that just like works in one shot, or like do your techniques break down or something?
Sorry, are you?
So what I'm saying is, D is in the denominator of the base of the exponent, right?
This one?
No, the other D, like LM over D.
This?
Yes, that D, right. So does your technique break down if D is bigger than LM? And in that regime, is there some alternative algorithm that just like samples in one shot or something?
Are you asking if when D is larger than LM?
Right, yes.
We can prove that it's impossible. The lower bound for, if we assume the distribution to have that two assumptions, LM should be larger than D.
Makes sense, thank you.
Okay, in that case, let's thank you, Joe.
Okay, thank you.
All right. Next up, we'll have Holden tell us about sampling using the basic score from multimodal distribution using database initialization.
Okay, great. This is joint work with Fred Kohler and Jun Wong, who is also here. Okay, so the general problem we're interested in is sample from a distribution given its density up to normalizing constant. The typical approach is with Markov chain Monte Carlo. We define a special random walk that converges to our distribution. This is Langevin dynamics on R to the D, or Glauber dynamics on a discrete product space. However, we run into trouble whenever we get a multimodal distributions because Markov chains tend to mix slowly. Okay, they'll get stuck in one of the modes and mix well in that mode, but fail to transition to the other modes. This is the phenomenon of metastability. There's various tempering or annealing-based methods, but these have guarantees only in special cases. And as the previous talk showed, we have hardness or exponential query complexity even for very simple distributions like a perturbation of a mixture of two Gaussians of equal variance. So what if we had more information? Let's suppose that we're given a small number of samples from this distribution, and our task is now to draw additional fresh samples from pi. Now, this is actually a very natural setting. It's a setting of generative modeling or distribution learning. Or given these samples, we want to learn this distribution and then generate fresh samples. In particular, this is the setting of score matching, where we use an estimated score function to run Langevin Monte Carlo. So our result is that given a Markov chain on pi, this is tractable under very general conditions and with a very simple algorithm, which is just start from a random one of these yi's and run the Markov chain for moderate time. This is a data-based initialization. Okay, so I'll give our main result and then two applications in continuous and discrete space. Okay, so the example that we want to tackle is that of a mixture distribution. Suppose our measure pi is a mixture of measures for which we know we have good mixing for Langevin or Glauber dynamics. Okay, we quantify this with a spectral gap. Now, this is an example of a more kind of general condition, which I'll introduce now, the case higher order spectral gap. So our general setting is we suppose we have a Markov process with a generator L and stationary distribution pi, and then this eigenvalues in increasing order, we assume a lower bound on the k plus 1th eigenvalue. Okay, this is, for convenience, I'm doing this in continuous time. If you're more familiar with discrete time, we can choose a step size t, and the discrete time Markov kernel is e to the TL, which has eigenvalues decreasing from 1, and the spectral gap is then a gap to 1. For k equals 2, we get the usual spectral gap, which implies fast mixing or exponential decay in chi-square divergence. Okay, and then this example fits this assumption using the Cron-Fisher variational characterization of eigenvalues, and this, in fact, extends to any generator L which decomposes into components. Okay, so to understand this condition, we can think about if we have a multimodal distribution, what are really our obstacles to mixing? If you look at the eigenfunctions, then you have kind of k bad eigenfunctions, which are ones which are almost constant on some of the modes. Okay, so our main result is the following, which is that given this kth order spectral gap, and given some samples from our distribution, suppose we start with this random draw from one of these samples and then run our Markov process for time t. Okay, so under the condition that we have a worm start under time t0 for any starting point, then with high probability, for a number of samples that's about approximately on the order of k over epsilon squared, and for a reasonable amount of time, then we can get TV distance that's epsilon close to our target distribution. Okay, so to understand this, note that this is really saying that we can sample from a distribution with k modes as long as we roughly have enough samples to estimate the relative proportions. Okay, because the sample complexity of estimating a discrete distribution with support size k is k over epsilon squared. Okay, and then to apply this theorem, we just need to find a reasonable bound for chi-square after a burn-in, and we can actually restrict this to a high probability set. Okay, so how does this proof go? The idea is that the only obstacle to mixing is this imbalance between modes, and we saw this is captured by these first k eigenfunctions. Okay, so we define a notion of a k epsilon eigenfunction balanced initialization, which is an initial distribution under which, if you look at the expected value of the vector of these first k eigenfunctions, that this is at most epsilon. Okay, the idea is if we have a sample of size k over epsilon squared, this is epsilon balanced between modes. We use concentration balance to prove this. And then starting from a k epsilon eigenfunction balanced initialization, we can get fast mixing to epsilon using eigenfunction expansion. Okay, so now let's see this applications to continuous and discrete space. So first, we have an application to Langevin dynamics with score matching. So this is a generic way to sample from R to the D that requires access to this gradient log PDF. Now, if we're only given samples, then if we can learn this score function, okay, then we can use Langevin dynamics to sample. Okay, this is the idea of score matching. Okay, so if we do Langevin with score matching, it's been observed that if you use an arbitrary initialization, you can get bad samples. However, if you initialize from data points, then you can actually get good samples. However, the samples worsen when you run MCMC for a long time. Okay, so this is consistent with the fact that the stationary distribution could be totally incorrect, but running for moderate time is good. Okay, so previous work by Kohler and Wang showed that you can't get good samples in this way, but you have some exponential dependence on the number of components. So we generalized the result to arbitrary mixtures and improved this to polynomial. Okay, so to state our result here, our goal is to given an estimate of the score function of this mixture and a few samples from this distribution, such that each of these distributions has good mixing for Langevin, we want to get a good sample in TV distance. So we can measure good mixing in two ways, using Poincare inequality or the stronger log Sobolev inequality. And the estimate we will assume on the score is this L2 score estimation error. Okay, so we exactly show this picture here, which is that under this Poincare log Sobolev inequality, we can get a solid TV distance with moderate time. Okay, so note that this does in fact have one part that is growing in time. This is accrued score error, and one part that is decaying exponentially. And then using the log Sobolev inequality, we can save a factor of the dimension. Okay, and then I'll note that there is an analogous theorem in the discrete case for pseudo-likelihood estimation, the discrete analog, and Glauber dynamics. Okay, so finally, I'll talk about last application over the hypercube, now in discrete space, to learning low complexity easing models. Okay, so the easing model is a model from statistical physics for distribution on the hypercube where we have these pairwise interactions given by a matrix J. Okay, and the goal is to learn this from samples. So previous works have tended to concentrate on the case where we have good mixing for this distribution. And in this case, we show that we can learn this even in cases where we don't have mixing in this low complexity or approximate low rank setting for J. Okay, so we'll use a result that approximately rank R Ising models are mixtures of distributions with good mixing. The number of mixtures is exponential in R. Roughly speaking, we can allow R eigenvalues that are outside the range 0 to 1. Okay, so in this setting, we can use the discrete analog of score matching, which is pseudo-likelihood estimation, okay, and then use Glauber dynamics to generate fresh samples. Okay, so given a number of samples that's exponential in this rank R, we can use pseudo-likelihood estimation and Glauber dynamics to produce fresh samples to within distance epsilon, and thus learn this distribution. Okay, so in conclusion, we show that we can sample from a distribution with k modes as long as we're given this information of these extra samples enough so that we can estimate the relative proportions. And in conjunction with either score matching or pseudo-likelihood estimation in the continuous and discrete cases, this allows learning multimodal distributions such as low complexity Gibbs measures. Okay, so there are some open questions. What's the power of Langevin with database initialization versus diffusion models? Here we cared about just generating additional samples, but you can also ask the problem of proper estimation for these models. And we can also consider weaker notions of a device, such as only having one sample from each mode. Thank you.
Do you think you can also get guarantees in KL divergency?
I think that should be possible, yeah, a bit more technical work.
Yes, so I was curious, is your condition on your eigenvalues, is it related to higher order Cheeger inequalities?
Yeah, so there's an equivalence actually is like the existence of this good partition with good mixing within the pieces. This is equivalent to a kth order spectral gap. Yeah, as a result by Oves-Garand, in a discrete case by Oves-Garand.
I have one more.
Yeah.
Is it clear that there's kind of like a hardness result if the rank is high, like with polynomial or with twice, samples from easy model? Like, is there kind of like a hardness for high rank easy models?
Not that I know of, and since our result, there has been actually some new progress on sampling for easing models, even in the low temperature setting. So I would check this.
Like just in general, like
yeah, learning, yes.
All right, let's thank Bolton one more time.
Which one is it? The first one? Okay, perfect.
All right, final talk of the session will be by Siddharth Mitra. It's going to be on characterizing the dependence of samples along Langevin dynamics and contraction of phi mutual information.
Hi everyone, I'm Sid and I'll be talking about this paper, which is joint work with Jiaming Liang and my advisor Andre Bisono. So let me jump straight in. So when we want to draw samples from a target distribution nu, we often construct a Markov chain, and the first question we ask is, what is the mixing time of this Markov chain? Because it tells us how many samples we should discard or burn in time when we want to use this Markov chains and actually get samples which have the correct law nu. In this talk, we are asking a slightly different question. We are asking how dependent is xj on xi? So what is the joint distribution of xi comma xj? And in particular, when is it, say, close to a product distribution? And as an example, so suppose you have data x1 through xn, which is identically distributed but potentially dependent, and you want to see how well this empirical distribution approximates the true distribution nu. So you can show that the smooth WP distance goes to 0 at the IID rate, but then there is also a further penalty for using the dependent data, which includes the pairwise Hellinger mutual information between the samples. And in our paper, we study the mutual information and generalizations to phi mutual information between samples along the Langevin dynamics, unadjusted Langevin algorithm, and the proximal sampler. And in this talk, I'll just be focusing on the ULA. So given some joint distribution rho xy, the mutual information is a functional of this joint distribution, and it's just the KL divergence between the joint and the product of the marginals. And the phi mutual information is what we get when we replace the KL divergence by a general phi divergence. So what is a phi divergence? So these are a family of divergences which are induced by convex functions phi, also called F divergences. And based on the F, we get different common examples such as TV, KL, and chi-squared. And needless to say, all of these mutual informations are 0 if and only if x and y are independent. So now let me talk about the ULA. So the Langevin dynamics to sample from nu is the following SDE, which has the correct target distribution as the stationary distribution. A simple forward discretization gives rise to the unadjusted Langevin algorithm. This is a biased discretization of the dynamics, so the stationary distribution is not the target distribution, and the mixing time of these Markov chains is very well studied. So our main theorem studying the contraction of information along ULA is the following. So suppose nu is strongly log concave and smooth. And also suppose that some marginal rho L satisfies a log Sobolev inequality, then we have exponentially fast contraction of mutual information in K minus L. So starting from the point that you have this log Sobolev inequality. And in fact, you can upgrade this to any phi mutual information if you have that the marginal satisfies a phi Sobolev inequality. And these inequalities generalize log Sobolev and Poincaré inequalities. And furthermore, you can also ensure that rho 1 itself satisfies the phi Sobolev inequality if you start your chain at a distribution which itself satisfies it, for example, at any strongly log concave distribution such as a Gaussian. Let me briefly talk about the proof sketch. So the proof sketch is based on data processing inequalities. So the naive DPI just tells us that information cannot increase along a noisy channel or Markov chain. The strong data processing inequality tries to quantify this and tells us when this inequality is strict. So in particular, now this is a function of the Markov chain P and also a distribution pi. So pi is fixed. It's the second input to this divergence. And then we take soup over rho and see what's the worst case ratio. And when this worst case ratio is strictly less than 1, then we have an SDPI for the tuple. And this ratio is called the contraction coefficient. So I claim that if nu is stationary for P and if P comma nu satisfies an SDPI, then we have fast mixing of P in phi divergence. And this follows by applying this SDPI k times, and each time you apply it, you pick up a contraction factor. And so you have this fast mixing. And SDPI-based methods have been used implicitly and explicitly to show mixing for many Langevin Markov chains. So now I'll talk about information contraction via SDPI and how this is different from mixing. So suppose U, X, Y forms a Markov chain, and the marginal of X is pi. Then we know that the SDPI states that the phi mutual information between U and Y is less than equal to the same contraction coefficient that we had before times the phi mutual information between U and X. And so now, suppose you have this Markov chain and you want to study the phi mutual information between x0 and xk. So you will instantiate this with u being x0, y being xk, and then x will be xk minus 1, and you will get this first inequality. And then when you do this recursively, you will get the product of these contraction coefficients. So as you can see that here, we need to control each of these contraction coefficients and make sure that they're all bounded away from 1. And this is the key difference between showing information contraction via SDPI versus mixing via SDPI. And so the main lemma which shows this, for example, for the unadjusted Langevin algorithm, shows that as long as the second distribution satisfies the phi Sobolev inequality, you can show that this contraction coefficient is strictly less than 1 and has this explicit form. And this is proven in the following way. So we will view the ULA update as a two-step chain. So there is the blue part, which is just the gradient descent part of the update, and then we are adding independent Gaussian noise to implement the Brownian motion. And in the space of distributions, the blue part is pushing forward the measure of rho k by this map I minus eta grad f, which I call G, and then the red part is convolving the distribution with the Gaussian. And in order to bound this contraction coefficient, so let rho be arbitrary, and we know that pi satisfies the phi Sobolev inequality, so we want to bound this ratio. And just applying the definition of what this Markov chain does, so this is the update in the space of distributions. And under the conditions here, so in particular when the step size of ULA is small enough, G is a bijective map. So this simultaneous push forward by G does not change the divergence. And then when we simultaneously convolve both by this Gaussian, we get contraction because of the contraction of phi divergence along simultaneous heat flow, which is what this Gaussian convolution is doing. And so to conclude, we study the contraction of phi mutual information for Langevin dynamics, the ULA, and the proximal sampler. The main proof technique is via SDPIs, and I showed this along the Gaussian channel for ULA in this talk, and it holds for via showing an SDPI for the forward and backward Gaussian channels for the proximal sampler. And for the continuous time dynamics, guarantees hold by taking suitable limits, or you can also compute the change of the phi mutual information explicitly. And thank you, and I'm happy to take any questions.
Questions for Siddharth? Okay, if not, let's retreat to the coffee break and
Thank you.
Siddharth one more time.